Now we try to solve another problem using the Rayleigh method. So the statement is that find an expression for the drag force on smooth sphere of diameter d moving with a uniform velocity v in a fluid density rho and dynamic viscosity mu. So now what we have to do is that we use the dimensional analysis Rayleigh method and we try to find an expression for the drag force. We already studied about this also in fluid mechanics 2, forces on immersed bodies. So I took these familiar examples so that you can understand that how effective dimensional analysis is. So this was the reason behind I took these familiar examples. So what we have to do is that first we write down the dependent and independent variables here. So Fd, the drag force, it is a function of the diameter d, velocity v, density rho, and dynamic viscosity mu. Then what we have to do is that this has to be written as a power equation. So we have Fd that will be equal to C, a dimensionless constant. So we have d power a, we have velocity v power b, we have the mass density power c, and we have viscosity that is power d. Now c is a dimensionless constant. Now again we use the MLT system. Again, I encourage you to solve these problems using the FLT system that you get the same answer or not. You must get the same answer. So let us use the MLT system. So we write down the dimensions for these quantities. Clear? So we have variable, let us write down SI units. Actually the units we write down so that we do not make mistake in writing the dimensions. We are more familiar with the units and we have the dimensions. So now we have this FD. So we already know that here the units are Newton, but Newton can be written as mass into acceleration. So consequently, we can write down the dimension as ml into t minus 2. Similarly, we have the diameter. So units are meter. This can be written as L. We have the velocity. So the units are meter per second. This can be written as L into t power minus 1. We have the mass density. So this is kilogram per cubic meter. So this can be written as m into L minus 3, and we have viscosity mu. So these units are, because this is dynamic viscosity, it contains the force units. So it is Newton second per square meter. These are the units. So this can be written as kilogram into meter per second square into second per meter square. So if you simplify this, what could be the dimensions? The dimensions will be equal to m into L minus 1 into T minus 1. So these are the dimensions. Now we put these dimensions in this equation here. So this will be equal to the force. Force will be equal to ml divided by T square, and this is power 1. This is power 1. This will be equal to L power A. You see here D. So L power A. C we do not write down because we already say that it is a dimensionless constant. Then we have V power B. So V is L into T power minus 1. So this is what we write down here. L into T power minus 1. This is power B. And then we write down here what is next, ml power minus 3. So this will be equal to ml power minus 3. This is whole power C, and then we have m into L minus 1 into T minus 1. This is whole power D. Now we have to satisfy the dimensional homogeneity. To satisfy dimensional homogeneity, the exponents of each dimension must be identical on both sides. So we can write down for m, we have 1 here. This will be equal to C plus a D. So let's say this is equation number 1. Then we have for L, so it is 1. Then L is A here. Then we have A plus B. Then we have minus 3C. And then we have minus a D. Well, let's say this is equation number 2, and we have for time t. So t here is minus 2 on the left hand side, and on the right hand side this is minus b. Time here is minus b, this is 1, and minus d. So let's say this is equation number 3. Now we have 3 equations with 4 unknown. You have 3 equations, 4 unknown, A, B, C, D. So it means that we must express 3 of the unknowns in terms of the fourth. Clear? So what we can say here is that solving A, B, and C in terms of D. This is an example. You can select others. So because we have 3 equations, 4 unknown, we cannot solve. So that's why you have to express the 3 in terms of the fourth. Let us we assume A, B, C in terms of D. So then what we will get? You will get A is equal to 2 minus D. B is equal to 2 minus D. You can solve. C is equal to 1 minus D. Clear? And D is equal to D because we express it in terms of the 3. So now we put these exponent powers here in this equation. So what we get that FD, thus that equation FD, the drag force, this is equal to C, dimensionless constant, into D power A, so it is 2 minus D. 2 minus D. Then we have the velocity V, it is power B, that is also 2 minus D. Clear? And then we have rho, which is power C. C is 1 minus D here. So we have 1 minus D. And we have mu, so that will be equal to power D. Now you just need to simplify this. So when you group the variables according to their exponent, what we will get? So from here, we get this FD, that will be equal to C into rho, you just simplify, into D square V square into VD rho divided by mu power minus D. We can just simplify the above equation to this. So you can see here we find something familiar. What is something familiar? That this VD rho divided by mu, this is something familiar, and this is actually Reynolds number. This is actually Reynolds number. You see that in dimension analysis, we come up and we find this dimensionless number Reynolds number. So it means that when we talk about the drag force, clear, on a sphere in a fluid, it means that the Reynolds number is important. So when we solve the similitude problem, there you have to identify for similarity laws which number is important: Reynolds number, Froude number, Weber number, Euler number. Now you see that the dimension analysis is telling you that which number is important. That's why dimension analysis is a very powerful tool. And once you identify this dimensionless number, then based on this, between the model and the prototype, we can develop the similarity laws, and we can transfer the results between the model and the prototype. So you can see how dimension analysis is important. That's why we need to study it. So this equation here, FD, this can be written as F prime now into R, because that is equal to Reynolds number. And we have rho d square v square. Or we can express FD divided by rho d square into v square, that is equal to F prime into R. So this indicates that the drag on a sphere is equal to some coefficient times rho d square v square. You see here, it means that the drag force on a sphere is equal to some coefficient into rho d square v square, where the coefficient is a function of the Reynolds number. Clear? Where the coefficient, that is a function of the Reynolds number. And actually, if we go back, what we studied in Fluid Mechanics 2 chapter, what we studied, that the drag force, if now we compare the results here in the dimension analysis with that, the drag force, it was equal to CD, the drag coefficient, times rho v square by 2 into area A. You remember this, we studied in Fluid Mechanics 2, forces on immersed bodies. So you can compare here. You see here FD divided by rho divided by V square, and it is area A for the general case. You see here it is D square. It is representative of an area. And this is a function of some coefficient. Actually, we know that that coefficient is the drag coefficient, and that coefficient is a function of the Reynolds number. This is what the dimension analysis is telling you. What we studied there, it is actually, CD is actually a function of the Reynolds number. And if you remember there, we developed, we studied the graph actually for the 3-dimensional and 2-dimensional objects. And it was this drag coefficient versus the Reynolds number. So you can see here that the dimensional analysis, it is very helpful. And another thing is that if you see here, this gives us results very familiar to this one. But still, you can see here that you ask a question that this half factor is missing. That's why I say that this dimension analysis, it does not provide complete solution. It provides partial solution. But that is also sufficient for us to understand the phenomena. That's why we see that this dimensionless constant we need to put. Because in the end, you do not get 100% exact equation. Clear? So that's why we put this dimensionless constant to take care of that. And in here, this dimensionless constant, clear, that we actually put in this here. Clear? So that's why when that coefficient we determine, which is a function of the Reynolds number, then we can get the exact functional relationship. So actually what we see here is that this C, this must be determined experimentally. Now in dimensional analysis, we come up to here. But in order to proceed further, then we have to determine experimentally the value here. You see, I write down here that f prime r, it means that there is some coefficient here which is a function of the Reynolds number. So that we say that this must be determined experimentally. So the conclusion here is that this dimensional analysis, that's why I consider these familiar cases, so that you can compare with what we have studied and then get idea that you can see here that this dimension analysis, although it does not provide 100% exact answer, the solution is partial only, but still you can see that it helps us to move in the right direction. That is why this dimensional analysis, it is a very powerful tool in fluid mechanics. Clear? Now, this was the Rayleigh method. We solved a few examples on this, but as I said that, as you can see here, if we have 4 unknowns, we have 3 equations, so we express the 3 in the form of the 4. So let's say in any fluid phenomena we have 10 variables, 20 variables, then it becomes very difficult to solve the problem using the Rayleigh method. Clear? Then it becomes very difficult to apply this Rayleigh procedure. Let me go back to in here. We discussed that we have 2 methods. So we discussed we have the Rayleigh method. Now in the problem you see that when we have 4 variables, so then we have to solve, and we are available 3 equations. So we express the 3 in terms of the 4th variable in order to simplify the problem. So this is actually the limitation of this Rayleigh method. That's why it is written in your textbook that although it is a very serviceable method, but it has been superseded by the Buckingham Pi method. So in Buckingham Pi method, any number of variables, we can solve the problem. So that's why in modern fluid mechanics books, the main focus is on the Buckingham Pi method. But we studied Rayleigh method also because it is given in your syllabus. So the next that we study, that is the Buckingham Pi theorem. Now a more generalized method of dimensional analysis developed by Buckingham and other. Actually, it was developed by several researchers, scientists, engineers, mathematicians, but the credit goes to Buckingham because he generalized the method that we apply today. So this arranges the variables into a lesser number of dimensionless groups of variables. So this is actually what I teach you in the previous lecture when I try to introduce the topic of dimensional analysis. You remember that there were 5 variables and we reduced to 2, and it reduced the greater number of experiments, save the time and the money for us. This is actually what is written here, that this Buckingham Pi theorem, it arranges the variable into a lesser number of dimensionless groups. This is what you will learn when we solve the problem. We actually reduce the number of variables into dimensionless groups. So it helps us to move in the right direction. It helps us to identify that what are the important dimensionless groups for this specific phenomena, and based on that we design our experiments. And based on that we develop the similarity laws between the model and then the prototype. So this is very important. Clear? But these are conceptual topics and you must have good understanding, otherwise you can make mistakes. Because Buckingham used an uppercase pi to represent the product of variables in each group, means the dimensionless groups. So he said, okay, in any fluid mechanics, any problem, you do the dimensional analysis and you get different dimensionless groups. So you get one group, you get two group. So he said, okay, let this be pi 1, let the other be pi 2, let the other be pi 3, and so on. So because he used this uppercase letter to represent those dimensionless groups, you will see in the method also when we solve the problem. So that's why this method is called the pi theorem or the Buckingham pi theorem, or we say the Buckingham pi method. So this theorem states that if there are n-dimensional variables in a dimensionally homogeneous equation, see PDH, principle of dimensional homogeneity, which is written in your textbook, PDH. So this is the foundation for these methods of dimensional analysis. So the theorem says that if there are n-dimensional variables in a dimensionally homogeneous equation described by m fundamental dimensions that we studied, MLT or FLT, described by m fundamental dimensions, they may be grouped in n minus m dimensionless groups. So it says that, let's say you have number of variables, that is, okay, n here, sorry, number of variables n, they are 5. Clear? In any phenomena, let's say for example, number of variables, dependent, independent, both, are 5. And all these variables, they have m mass as dimension, they have length as dimension, they have t as dimension, or in the FLT system, it means all the three are present. So m will be then equal to 3. So the theorem says that they may be grouped in n minus m dimensionless combinations. It means that 5 minus 3. It means that in that problem, if we have number of variable 5 and m is equal to 3, it means that there will be two dimensionless groups, whatever. That way one will be pi 1 and the other will be pi 2. If in any problem you have n is, let's say, equal to 7, and all of the fundamental dimensions are present, m will be 3, so 7 minus 3, it means there will be 4 pi groups you need to make, pi 1, pi 2, pi 3, and pi 4. This is what the theorem says, that we can reduce the number of variables from 7 to 4 dimensionless groups. This is the advantage. Clear? So you will see in the problem how we apply these. This is the Buckingham pi theorem. So now let us see that how we apply this method to solve the problem, analyze the problem, this dimension analysis. Clear? So actually, this Buckingham pi theorem that we just explained, that we reduce from 7 to 4 or from 5 to 2, in most cases this will be true. In some cases this may not be true. That I can give example. But in general this is true. That's why we defined this theorem. And remember, there is a proof of this theorem, but that is not as simple as this theorem. That is very difficult to understand. That is beyond the concept, you can say the contents of even our textbook. In advanced books, you can find the proof of this theorem, which is not as easy as the theorem itself, but there is a proof available. We can prove this theorem. Let us not focus on the proof. So in general, this theorem that it help us to determine that how the number of variables we can reduce Clear? This we can do by different ways now. This we can do by different methods. But we will just focus on one method to do it. That is given in your textbook. As I said before, I will try not to go beyond the textbook, just to keep it as simple as possible for you, since you study other courses. So to come from 7 to 4 or 5 to 2, this is 2 here, 5 to 2, this we can do in several ways. One of the method, which is systematic method, step-by-step method, that we will explain, this is known as the method of repeating variables. This is what we will study, and this is what is given in your textbook. So according to that method, step number 1 is visualize the physical problem, consider the factors that are of influence, and list and count the n number of variables. How many variables are there? 2, 3, 4, 5. So you can see here that the first step is, if you have any problem, you have to identify how many variables are there. It's not like a question that the variables are already given. This is general problem. You are a researcher and you are working in a new fluid phenomena where we do not have any equation, any theory, any experiment. So you have to identify what are the variables that need to be considered. That's why I said before, I repeat, if you miss important variable or you bring unimportant additional variable, the work will increase to no benefit. So that's why I'm saying again that these are conceptual topics. If in the step number 1 you make a mistake, so definitely the results obtained will be incorrect. So visualize the physical problem, consider the factors that are of influence, and list and count them. Because we are learning this, so that's why in the problems these variables are given to you. Step number 2, choose a dimensional system. Either you use the MLT system or FLT system. You will get the same result. So this is not a question that when you solve a problem that should I use MLT system or should I use FLT system. This is not a question. You will get the same result. And list the dimensions of each variable. Find M, the number of fundamental dimensions involved in all the variables. So you will calculate mass is present, length is present, time is present, M is equal to 3. If 2 are present, M is equal to 2, like this. So the next step would be choose the system and calculate the number of fundamental dimensions present in all the variables that you identify in step number 1. In step number 3, we find the reduction number k. This step is given because sometimes in the problem, actually what the theorem says you take n minus m. Fine, in most of the fluid mechanics problem this is okay. But sometimes there are rare cases where this k, it usually equal to m. It cannot be more than m, but very rarely it is less than m. I will give an example if time is available. So you will see that why we need to calculate the reduction number k. In most of the problems in fluid mechanics, we are discussing only fluid mechanics point of view, this dimensional analysis. So in most of the time in fluid mechanics problems, this k will be equal to m. So whatever is m, just k take equal to m. There are some rare cases where k will be different than m. I will give example later on when we have time available. So there then you can see that if we take k equal to m, we will not be able to solve the problem. So in that case, then we reduce the k by 1 and try to solve the problem. So that's why in your textbook this is written. Maybe this step you may not find in other fluid mechanics books. But we try to cover every aspect. So that's why with the step number 3 will be to find the reduction number k, which will be most of the time equal to m. In very rare cases, it may be different than m. I will give example if we have time. It's easy. So step number 4 will be determine n minus k, the number of dimensionless groups that are needed in that problem. This will be step number 4. For example, like I did here, n is equal to 5, m if it is equal to k, so 5 minus 3 means you need 2 dimensionless groups to solve the problem. For example, here you need 4 dimensionless groups, pi 1, pi 2, pi 3, pi 4 to solve the problem. This is what we say here. Determine n minus k, which is usually equal to m. So this will give us the number of dimensionless groups that are required to solve the problem. So this is the first question that we will try to answer, that how many dimensionless groups are required? How many? That is answered by this Buckingham-Pi theorem. This is coming from the Buckingham-Pi theorem here. This is, we defined it here, see? And then the next question that we would like to answer, what are they? Is it an odd number that we come up? Is it a Froude number that we come up? Is it a Weber number that we come up? What are they? So these two question answers we are looking for in these methods. Step number 5 is that from the list of dimensional variables, select k, which we already determined, them to be called the primary or repeating variables. This is the tricky step in this method and the important step in this method. For example, we have 5 variables, that is n is equal to 5, and let's say you calculate k is equal to, let's say, 3. K is equal to 3. So it means we have to form 2 pi groups, because n minus k is 2 pi groups that we have to form. And remember, these are dimensionless groups because pi has no dimensions. So in here, you will write down these 3 variables, which we call as primary variable or repeating variables, that will repeat here in both the dimensionless groups. This will be 3 plus 1 from here, because 2 are remaining. Out of 5, 3 are repeating, 2 are remaining. So from 2, 1 will come here, and then 1 will be coming in the second pi group here. You will see this when we solve the problem. 1 will come here. So because these 3 are repeated in both the groups, if we have 4 groups, these 3 will be repeated in 4 of the groups, depending on the problem nature. So because they are repeating, that's why this is known as method of repeating variables that we follow in the Buckingham-Pi method. By the method of repeating variables. But there are other ways also to solve using the Buckingham-Pi method, but these are not included in your textbook. So we will just follow this method here. Now the next question is that if these 3 are going to be repeated here and here, how to select them? Out of the 5, how you know that these 3 should be the repeating variable? That's why this step number 5 is the tricky part of this method. So there are some guidelines which are given that we need to follow as far as possible. Then we can finish this step successfully. What are the guidelines? Some are given. This is from your textbook. And some other guidelines I will also share that is taken from another book that will help us to identify that how we select the repeating variables. So your textbook says that these must contain all of the m fundamental dimensions. When you select them, you should ensure that they contain all of the fundamental m dimension. Means they should contain mass, L, and time preferably. Remember, these are guidelines. Follow as much as possible. And these must not form a pi group among themselves. Why? Because if these 3 form a pi group, if you combine with one more, how you will make a dimensionless pi group? It will be not possible. So that's why, because this 3 into 1, these 4 together should make a dimensionless group. This is what pi means, that it is a dimensionless product group. So when you select the 3 among themselves should not make a dimensionless group. But when it combined with the other remaining 1, it should make a dimensionless group. So this we have to select in this fashion. Generally, it helps to choose primary variables that relate to mass, geometry, and kinematics. You should preferably take from each of these groups if 3 are to be selected. The reason is that, let's say for example, if you select diameter and then it is also present length L as a variable. So do not select both at the same time, because you see L by D or D by L, it forms a dimensionless product or group. So it means that you should select only one from this. Either select D or select L. So when we solve the problem, you will further understand. And also, the selection of these 3 is not unique. That always we have to take these parameter as repeating variable. It will depend on the nature of the problem. So that's why this step number 5 is the most difficult and tricky part of the method. So once you select, then form the pi groups as I write down here by multiplying the product of the primary variables that we select with unknown exponents by each of the remaining variables one at a time. Means from the remaining 2 here, make it 4. This will be a product, clear? Not, you don't have to add them. I'm saying this is a 4. So the 4 variable you have to group with unknown exponents like we did in Rayleigh method, and 4 here. So it means 3 with the one remaining, 3 with the other remaining, like this. If we have 5 variable and 3 are to be selected as repeating, this is what we have to proceed. But the numbers can change from problem to problem. So we will solve problem, you will better understand what I explain here. Step number 6 will be to satisfy the dimensional homogeneity. This is what I say already, that the foundation or basis of these methods is dimensional homogeneity. Equate the exponents of each dimension on both sides of each pi equation and solve for the exponents and forms of the dimensionless group. This is actually what we did in Rayleigh method. That is what we have to do here. And the final step number 7 is that rearrange the pi groups as desired. As I said that the pi groups, the dimensional analysis does not provide 100% solution. So that's why we can arrange these pi 1, pi 2, if we have pi 3, pi 4 also, as desired. We can manipulate them to get the required result. That's why these are conceptual topics. You must understand. The pi theorem states that the pi's are related and may be expressed as like this. Because the number of variables that have to reduce from n to n minus k, where k is the reduction number, that's why you see the pi's, they are up to n minus k. And the theorem says it can be written in this fashion: pi 1 as a function of the other, or you can write down pi 2 as a function of the other, or you can write down pi 3 as a function of other. This we can manipulate. That's why it is written that rearrange the pi groups as desired, because we want to get the required result. Clear? So that's why you can see here that this, it does not predict the functional form of F1 and F2, because now here it changes. So that's why we have F1 and this is F2. From where this F1 and F2 will come, these relations must be determined experimentally. So that's why this dimensional analysis does not provide complete answer, but no doubt you already saw from the Rayleigh method, it gives us the correct direction that we should proceed. So we can raise each pi parameter to any power as required, and this will not affect their dimensionless status. You must understand very well these concepts, then you can successfully apply these methods and get the results. Dimensional analysis, this is what is written in your textbook, does not provide a complete solution to a fluid problem. It provides a partial solution only. The success of the dimensional analysis depends entirely on the ability of the individual using it to define the parameters that are applicable. So the success of the method depends on your ability to define the parameters that are applicable. If an important parameter is omitted, then the results are incomplete, and this may lead to incomplete conclusions. Clear? So these are some guidelines which I took from another textbook for choosing the repeating variables. These are some guidelines. Follow as much as possible. If not, so just do it how to get the required result, because you, in the end, you can determine that you are moving in the right direction or not. So guidelines, some guidelines for choosing repeating variables in step 5, which is the tricky and difficult step in the method. So that's why this is known as method of repeating variables. Try never pick the dependent variable, because then it will appear in all the pi groups, that is undesirable. Follow as much as possible. But if you see the solved example in your textbook, discharge on a spillway, that is taken as a repeating variable, which is a dependent variable. So then you will say that why it is written here, never pick the dependent variable, otherwise it may appear and it is undesirable. So these are guidelines. Avoid as much as possible. The chosen repeating parameters must not by themselves be able to form a dimensionless group. Otherwise, it would be impossible to generate the rest of pi. This is what we already discussed. Among themselves, the repeating variable should not form a dimensionless group. The chosen repeating parameters must represent all the primary dimension in the problem. This we already discussed. Never pick parameters that are already dimensionless. These are pi's already by themselves. For example, you have theta as a parameter in any problem. So theta has no dimensions, clear? So this is already one of the pi group. Don't consider it as a repeating variable. Never pick two parameters of the same dimensions or with the dimensions they differ only by exponent. I already explained that if you have, for example, diameter in a variable, length as a variable, don't pick both at the same time. Just pick one of them. Either pick D, solve the problem, or pick L and solve the problem. This selection of repeating variable is not unique. So pick one of them, don't pick both at the same time. This is what this guideline says. Never pick two parameters with the same dimensions or this at the same time. You can choose one of them. Whenever possible, choose dimensional constants over dimensional variables so that only one pi contains the dimensional variable. It says that, for example, you have acceleration due to gravity. This is dimensional constant, clear? So it says that try to select these as the repeating variables wherever possible. So remember, these are guidelines. Follow as much as possible. Sometimes in some problem, if we have to avoid them, then fine, like I explained here. Now in this here, it is written never pick dependent variable. You see the solved example of your textbook. The dependent variable is taken as repeating variable and the problem is solved. So just follow them as much as possible. Maybe in that case we need to take, but in other cases we should avoid. So these are guidelines how to select the repeating variables in the Buckingham Pi method. So the method of repeating variables cannot predict the exact mathematical form of the equation. This is what I already explained. This is the fundamental limitation of dimensional analysis and the method of repeating variables. So although it does not provide 100% exact solution, but still you saw from the problems that we already solved that it helped us to move in the correct direction. So that's why we cannot say that we should not use it. Still, it is a very powerful tool and it is used in the research work. So let us try to start with a problem, then I will stop somewhere and we will continue in the next class because we have limited time. So let us start, then I will stop somewhere and we can continue. Find an expression for the drag force, the problem that we just analyzed with the Rayleigh method. Now let us try to analyze the same problem by the Buckingham Pi method and see what we get. On a smooth sphere of diameter d moving with a uniform velocity v, the fluid density rho and dynamic viscosity mu. So we go step by step procedure and we follow the method of repeating variables. Remember, if we follow the Buckingham Pi method, there are several procedures to solve. So the method that is explained in your textbook, that is the method of repeating variables. So let us follow this. We will stick to the textbook. So first, step number one is that we identify the parameters that are significant in any fluid problem. This is step number one. So luckily, because we are learning at this stage how to apply the method, the parameters are given to you. So this step is already done for you. Otherwise, if you are doing a research and you do not have any theory for that, you have to identify the important parameters and solve the problem. So we have F D, we have the diameter, we have the density, we have the velocity, and we have the viscosity. So we identify the parameter. Dependent, independent, so it says that you count them. So we have how many? We have 5 variables total. Next we go to the step number 2. This is actually very important if you are a researcher. You do not have any formula, you do not have any idea about this from previous. So this will be your job to identify important parameter. If you miss important parameter, then definitely you will follow the procedure, but you will not get the correct results, incomplete. Or if you bring unimportant another parameter, you see it will increase the work but of no benefit. So that's why this step is very important. Step number 2 is that we select the system. So let us choose, either you use the MLT system or FLT system, you will get the same result. I encourage you to solve by both as a learning exercise. So select, you want to follow MLT system or FLT system. So you will list the dimensions. For example, we already write down this. I will quickly write down here. So f d, we already write down that this is ml by t square, and we have the diameter dimension is L. We follow the MLT system. You can use the FLT as a learning exercise. We have the velocity. You see, some problems when you use MLT system is more convenient. Some problems when you use FLT system more convenient. That's why we have these options available. But you must get the same result. This is for sure. This is L by T. Then we have the density. We have m by L cube, and we have the viscosity. Its dimensions are m divided by LT. So now you can see that M, L, and T are involved. So it means that you see all the three fundamental dimensions are present. M is present, L is present, T is present. So that's why M is equal to 3. If 2 were present, then M will be equal to 2. This will be step number 2. Then step number 3 is that we have to find the reduction number K. Step number 3 is find the reduction number K. Now this K, as I said, most of the time it will be equal to M. So here we identify that, for example, if I consider rho Vd, it cannot be combined to form a dimensionless group. You take the product, you take the numerator, denominator, divide by anything. We cannot make a dimensionless group from these three. For example, this is just an example. So it means that this K will be equal to 3. I am saying in other words that this K is equal to M. Clear? Because in here velocity, density, and the diameter, all the three are present. You see, all the three are present. L is present, M is present, and T is present. So you can see here, if you combine rho Vd, M is only in rho. How it will cancel out by D and V. So based on this, we say that M is K is equal to 3. In other words, it is M equal to 3. We are just try to justify this reduction number K. Okay, so K is now 3. Then we move to step number 4, and we determine how many pi groups are required to solve this problem. Step number 4 is that how many pi groups are required to solve. So this is easy because we say that number of pi groups needed, number of pi groups needed, that is simply equal to n minus k. If you write down n minus m, still it is fine as we defined in the theorem, but maybe in very rare cases m and k will not be same, so that's why we prefer to use k. I can give you example where you will see that why we need to use k rather than m. So now from here, n is 5, k is 3, so it means we need 2 pi groups to solve this problem. It means that we need the uppercase pi 1 and uppercase pi 2 to solve this problem. So now, as I said, How many dimensionless groups? 2. And this is coming from the Buckingham pi theorem. So now it means that these 5 variables present in the problem, we can reduce them to 2 dimensionless groups. Step number 5 is, this is the important step, the tricky and difficult step. Now we have 5 variables and we need to make 2 pi groups. So it means that k number of variables you need to select as repeating variables, because this is, we are applying the method of repeating variables. So it means that in the 2 groups, 3 will be repeating in both. So it means we have to choose, and the guidelines are already given to us that we just learned in the previous slides. So let us take, based on that, let us select a row V and D as repeating variables, because they satisfy the concept we say that should be from mass, geometry, and kinematics, as written in your textbook. Now the question is that, will these be always repeating variables? No. Will always you select row VD as repeating variables? No. When we finish this problem, then I can tell you, if I take other than these as repeating variables and solve the problem, still you should get the same result, but the functional relationship will not be exactly the same. So here we just say that, okay, let me select these 3 as repeating variables. But you can also take other repeating variable following the guidelines, not just blindly, correct? Otherwise, you will get incorrect solution. So following the guidelines, we select them these 3. This is actually the most difficult step in the question. So these are repeating variables. Let us solve this problem, then I will discuss this step again. If I take other, what will be the situation? So this is coming. So once we select these 3, you will form the 2 pi groups. One is pi 1, the uppercase we use to denote. So that will be equal to rho, and because we have to assign the power A1, and then we have the D, let me take D, this is B1, and we have velocity as C1, because we have 2 groups, so A1, B1, C1. You use X, Y, Z, no problem. And one of the non-repeating variable. And the second one will be then equal to the repeating variable. That's why this is known as method of repeating variables. Then we have A2, then we have the diameter B2. You can write down here XYZ, no problem. Then we have this as C2, and we have FD, remaining variables, one of remaining. This is how we make these 2. So now, because we assign these arbitrary exponents, we need to calculate their values like we did in the Rayleigh method, using the principle of dimensional homogeneity. So step number 6, let us try to continue for this one, then I will stop it here, the lecture. We will continue in the next class. So this step number 6 is, we will now calculate these exponent values for each of the group. So let me just do it for one, then I will stop it. We will continue in the next class. So what you will do is that we will satisfy the dimensional homogeneity. So let me just quickly go for pi 1. So you will do it like this for pi 1. Now, what is pi 1? It is equal to rho a1 d b1 v c1 and mu. We already write down their dimensions here. From here you will pick the dimensions. Step number 2. And you will write down it here. How to write down? Because pi is dimensionless. So we can write down this pi is m power 0, L power 0 and T power 0. This is pi. Pi can be written like this because we already say pi is a dimensionless. And on the other side it will be equal to m by L cube into a1, then we have L power b1, then we have velocity L by T power c1. This I'm using here, this equation here. I just put the dimensions here. And we have mu. So we have mu that is equal to m by LT. And you already know the power is 1 here. Now we just principle of dimensional homogeneity. So we say that for m, just like we did in Rayleigh method, this is 0 here. So 0, m here is a1, m here is a1 plus 1. Let's say this is equation 1. Then for L, so L is 0 here, left hand side, right hand side. So this L here, what is L3? So minus 3a1, L here plus b1, then we have c1 and L here minus 1. Let's say this is equation number 2. And for T here is 0, T here is minus c1 and T here is minus 1. Let's say this is equation number 3. So solving for the 3 unknown, just like we did in Rayleigh method, same here. Now solving a1, this comes out to be, you have to calculate its value. So in this case, this a1 comes out to be minus 1. b1 comes out to be minus 1. And you can see here c1 comes out to be minus 1. So now we put these in the values. We already know that pi 1, that is equal to a rho here, rho. What is a1? Minus 1. Rho minus 1. Next we have d, power b1. What is the value of b1? Minus 1. Next we have v, velocity, power c1. So what is c1? It is minus 1. And we have mu, power 1. So this can be written as mu divided by rho dv. Now when you get here, you must satisfy that you should get no dimension. You should not get no dimension. If you get any dimension here, you have made a mistake here. Go back, because the definition of pi is dimensionless. This will be a check on your calculations. You put the dimensions of these quantities and you should not get any dimension remaining. All should cancel out. If you have any dimension remaining, there is a mistake. Now we identify that this rho vd and this mu, it makes something familiar. it makes something familiar, because we already know that this rho Vd by mu, this is something we already know that this is actually a Reynolds number. You see, this is how dimension analysis help us to identify what number is important for that problem. This is the power of this dimensional analysis, even though it does not provide complete solution. So we can write down this pi 1. So this means Reynolds number, it has no units. It means this is correct, no dimensions, because we already know Reynolds number has no dimension. So this is a check on the calculations. So this pi 1, it can be written as R inverse, because this R inverse. And similarly, we proceed for pi 2 and then try to write down the functional relationship. So we will continue with this in the next class.